Hi everyone, in this video we will discuss about the analysis of shear. Generally, shear develops due to either bending or twisting. Shear stresses are classified into two types. First one, flexural shear stresses. These flexural shear stresses will be developed due to the bending. And the second one is torsional shear stresses. These torsional shear stresses will develop due to the twisting, right, or torsion. Here I am taking a prestressed concrete beam of size b by h. Small b is the width, small h is the height of this beam. If you observe, there will be two stresses. One is the normal stress, another one is shear stress. Across the section, means across the depth, normal stress may vary and shear stress may vary, and along the length also shear stress this shear stress may vary and bending moment also may vary. That's why at every point there will be a combination of stresses in length direction and stresses in y direction. Suppose if you observe at neutral axis at midpoint, I am taking a point at this point. At this point, normal stress is 0, but shear is maximum. Normal stress is 0, shear is maximum. If I take somewhere here, there is some normal stress and there is shear stress. Here also you can see at this length there is some shear and there is some bending. That's what I am telling. There is a variation in normal stress and shear force in both length direction as well as depth direction. The combination of normal and shear stresses generate two-dimensional stress field at a point. These forces will develop two-dimensional stress system at a point. At any point in the beam, the state of two-dimensional stresses can be expressed in terms of principal stresses. The Mohs circle of stress is helpful to understand the state of stress. Right. If we consider an element 1 on the neutral axis, the stress system will be like this. Here you can see I have taken the element on neutral axis. On this element, the shear is maximum, but that at neutral axis the normal stress is 0. See, normal stress is 0. Here I have shown only the shear forces. Here I have shown only shear V. We may call this state as pure shear state. Why? Because only shear is acting on the element. There is no normal stress. This state can be called as pure shear. Right? See, at the level of neutral axis, we may get the state of pure shear. A state of pure shear can be conceived as a state of biaxial tensile and compressive force. These principal stresses are inclined at 45 degrees to the neutral axis. Right? These principal stresses are, as I said, due to this pure shear state, there will be two principal stresses, tensile and compressive stresses. Sigma 1 is tensile, sigma 2 is here it is like this, sigma 2 is compression, okay. This is compression, this is tension, right? There will be two stresses, that's why we may achieve a state of biaxial, tensile and compressive stresses. These principal stresses are 45 degrees with the respect of axis of the beam. It is necessary to understand the principal stresses to understand about the cracking of concrete. The Mohr circle is a representation of the state of in-plane stresses on the surfaces of various inclinations passing through a point. The horizontal and vertical axes represent normal stresses and shear stresses respectively. Right? This horizontal axis will represent normal stresses and this vertical axis represents shear stresses. Right? As we observed, in this case normal stress is 0. But there is a shear. That's why I represented the shear. Since the shear force is maximum near the support, the crack due to shear occur near the support. Generally, at support, if you observe, this is a simply supported beam. Let us assume this is simply supported beam. The shear is maximum at supports. As the shear force is maximum at the supports, crack due to shear occurs near the support. The cracks are formed around the neutral axis. Means under perpendicular to the principal stress. Means the crack will be like this, perpendicular to this one. The crack will be like this, crack will be like this. We may observe this type of cracks. In this case. Now I am taking an element 2 at bottom edge which is under tension. The tensile stresses due to flexure, is maximum and shear stress is 0. The state of stress is nearly uniaxial tensile stresses. Means the compressive stress is 0 at this case. That's why the Mohr circle is shifted towards axis of principal tensile stress. You can see here. This is the element 2. Here we are having both shear and the axial stress F on the same element. Due to this one, we may observe only tensile forces. The compression forces are almost negligible, and the angle alpha is less than 45 degrees. That's why in Mohr circle you can see only a sigma 1 and sigma 2. Tensile forces are almost zero. Right? Since the movement is maximum at midspan, crack due to flexure occurs nearly midspan. The cracks are formed at the bottom edge and perpendicular to the sigma 1. We will see. Suppose in this case we may observe cracks like this. we may observe cracks like this. The stress will perpendicular to this one, means like this. Here this cracks will be like this, right? As the movement is maximum at midspan, cracks due to flexure occurs nearly at midspan. The cracks are formed at the bottom edge and perpendicular to the sigma 1. Since sigma 1 is parallel to the edge, sigma 1 is parallel to the edge, sigma 1 is parallel to the edge, the cracks are perpendicular to the edge. Okay. Coming to the types of cracks. Types of cracks. The type and formation of cracks depends on the span to depth ratio of the beam and loading. Span to depth ratio of the beam and loading conditions. And loading. These variables influences the moment and shear along the length of the beam. For simply supported beam under uniformly distributed load without prestressing, we may have three types of cracks. First one, flexural cracks. Second one, web shear cracks. And third one, flexure shear cracks. Both flexure shear cracks. These flexural cracks form at the bottom near the midspan and propagates upward. Suppose this is the beam. Okay, these cracks will develop at bottom near the midspan and propagates upwards. These web shear cracks, this crack generally develop near neutral axis. Suppose this is the beam, we may have the neutral axis somewhere here. These cracks form near the neutral axis, close to the supports and inclined to the beam axis. Means it may web shear cracks will be like this. And third one, web shear cracks will always very nearer to neutral axis. Third one, flexure shear cracks. Flexure shear cracks form at the bottom due to flexure and propagates due to both flexure and shear. Suppose, see, this is the beam. Initially, flexural cracks will develop. Over the time and influence of loading and propagation of cracking, the shear will also influence on these cracks. It will take shear cracks, like it will just bend with the angle of 45 degrees. We may call it as a flexure shear cracks. Okay, these cracks form at bottom due to flexure and propagates due to both flexure and shear. Generally, beams with a low L by D ratio and inadequate shear reinforcement, we may observe generally 5 types of failures due to shear. First one, diagonal tension failure. Second one, shear compression failure. Shear compression failure. Shear tension failure. Shear tension failure. Fourth one, web crushing. And the fifth one, arc rib failure. Rib failure. Generally we may observe this type of failures. Coming to first failure, diagonal tension. Diagonal tension failure. This type of failure induces an inclined crack, propagates rapidly due to inadequate shear reinforcement. Suppose this is the beam, this is the beam, this is the support. Here we have some load. This type of failure, generally there will be a crack. There will be a crack like this, but this total beam will fail in shear, means it will come down. This total beam come down like this. Cracks will be like this. Shear cracks. This is diagonal tension failure. In this case, the inclined cracks propagates rapidly due to inadequate shear. Next, shear compression. Shear compression means, I will show here. In shear compression, there will be a crack, but at the tip of the inclined crack there will be a crushing of concrete. This is known as shear compression crack. This crushing will be in shear zone. Next, shear tension. Due to inadequate anchorage of longitudinal bars, the diagonal cracks propagates horizontally. So here we have inclined crack, right? Due to inadequate anchorage in longitudinal reinforcement, these cracks will propagate horizontally along the bars like this. Here we may have longitudinal bars. The crack will develop horizontally like this. This is shear tension. Next one, web crushing. The concrete in the web crushes due to inadequate web thickness. If we provide the web thickness is less, then we may observe some crushing in the web zone. Suppose I am taking some I section gutter like this. Okay, here we may observe some crack. Here we may observe failure, crushing of the concrete. And the last one, arc rib failure. Suppose this is the beam. Here we have support. For deep beams, the web may buckle. If web is thin, then it may crush. If we are having sufficient width of the beam and we are not provided adequate shear reinforcement, then the web may buckle and subsequently crush, right? Then there can be a anchorage failure or failure of bearing as well. Here, due to inadequate reinforcement in the web, along with the crushing, there will be some buckling, and this may induce failure of the bearing also. There will be a crushing at supports as well. We may call it as a rib failure. Now we will see the effect of pre-stressing on this stress system, principal stress system. Okay, suppose in earlier case, this is we have taken a normal RCC beam with breadth B and height H, right? We have taken an element at neutral axis. In that case, so we will recollect what we discussed in that case. We observed a pure shear system. In the system, angle is 45 degrees. Angle is 45. This principal tensile force is making an angle 45 degrees. In Mohr circle, 2 alpha is exactly 90 degrees. When we apply a precessing force, here, suppose if we apply precessing force here, there will be a normal stress, right? In this case, okay, it is not pure shear, means here we are having only shear forces, no normal stress. If you apply a precessing force there, then there will be a normal stresses also on the element. When the normal stresses will act, then this total element will move and make an angle greater than 45 degrees. This angle will become greater than 45 degrees. And this alpha is not 90. It will be greater than 90. Right? What happens here? The stress system will be, suppose this is the element 1 on precessing system. Here we may have shear. In addition, due to prestressing, there will be prestressing normal forces on the element. Due to this normal force, the principal tensile force earlier, this principal tensile force makes an angle 45 degrees, but this angle is not now not 45 degrees, it will be greater than 45 degrees. And earlier in Mohr circle, it is making an angle 2 alpha. Now it won't make that angle. This angle will be greater than 2 alpha. 2 alpha is greater than 90 degrees. Right? See, the formation of cracks for a precessing beam with large span to depth ratio and uniformly distributed load will be less compared to RCC. Obviously, if you observe in this case, the cracks will develop, but it may not propagate much. It may not propagate either flexural cracks or flexural cracks or shear cracks, whatever. It may not propagate. Right? After cracking, in the presence of prestressing force, the length and crack width of diagonal cracks are very low. The aggregate interlock and zone of concrete under compression are larger as compared to non-prestressing beam under the same load. Hence, the shear strength of concrete increases in presence of prestressing force. Right? The shear strength of concrete increases due to prestressing force. Due to prestressing force. Right? Thank you.